Well, hello everyone in quarantine land. Today we're going to do a quick video lesson on simplifying radical expressions. So let's look at the homework assignment that came in that's driving this video. See here we have to simplify some radicals and we have to solve some equations, and since the directions say simplify irrational solutions, we're going to use a radical somewhere in here. We're probably going to take the square root to get to our final answer. And then this is a little outdated, a little archaic actually. It says simplify, and then it references using a table of square roots as necessary. So what that tells me is in the back of this textbook, there's likely a table of the square roots of non-perfect squares and their approximation rounded to 4 digits or whatever. We're not going to do that. It's 2020. We could use a calculator, but I will in this video show you how to quickly estimate non-perfect square roots, just in case you have to. All right, so let's get started. What in the world is a square root? Well, you've likely seen this symbol right here. This symbol, notice there is no number here. It is just this symbol alone with no digit or number right here in this crevice. This symbol is called a radical symbol, also referred to as square root symbol or a radical sign. And we use it to represent the square root of a number. Now, you will see these symbols with numbers here. You could have a 3 here. Whatever number is here indicates what root we're taking. We are only working with square roots in this video because that's the question that was asked of me. So if there is no number here, we are dealing with a square root. And that's all we're going to do in this video. So what is a square root? Well, square roots, as well as all the other roots we're not going to talk about, are very closely related to exponents. Let's look at an example. If we have 5 raised to the second power, we know that equals 25. We also know that the second power is referred to squaring. So this equation reads 5 squared equals 25. In fact, if you have 2 factors of 5, you do have 25. 5 times 5 is 25. Well, square roots are simply the inverse operation. And when I say inverse, just think opposite of squaring. So square roots are the inverse operation or the opposite operation of squaring. So if you want to undo squaring, we squared 5 and got 25. Well, if you want to undo squaring, you have to square root. So the square root of 25 asks what number raised to the second power gives me 25, right? So to sum this all up, the square root of 25 is equal to 5 because 5 is the number that when squared gives you 25. All right, so what's the first place you're probably going to see these in a textbook? You've learned about square roots, now you're going to see some word problem. It's probably going to look like this. It'll say a square bulletin board or a square table or a square picture or square anything is completely covered with 9 square feet of paper. That is telling you the area of that square is 9 square feet. And then it asks, how long are the sides of this bulletin board? So let's put a visual up. The key here is that it is square. And so all the side lengths are the same. And they've given you the area. The area here is 9 square feet. So all we really have to do is remember the formula for the area of a square. And that says area is equal to the side length squared. You could say side times side, but I'm trying to get at whole squaring and square rooting being opposites. So we're going to go with area equals side squared. All right. So if the area is 9, we know 9 is equal to the side length squared. If we wanted to solve for 9, and let's say we didn't already know that, yes, 3 squared gives us 9, and therefore the sides of this bulletin board are 3. If we actually wanted to use inverse operations, because at some point we'll need to use inverse operations. We need to remember that taking the square root is the opposite of squaring. So when I want to get this variable alone, I have to do whatever is the inverse operation of what's with it. Well, what's with it? It's being squared. So I have to square root both sides. So I'm going to take the square root of both sides. Square root of 9 is 3, and bear with me there. And the square root of s squared is s. Notice that squaring and square rooting are opposites. So once I square root something raised to the second power, they cancel each other out. They're opposite or inverse operations. They will cancel each other out. I am just left with s. Now let's talk about the square root of 9. Technically, the square root of 9 is positive and negative 3 because the quantity negative 3 squared is also 9. But since this question is asking about a side length of a bulletin board, it can't be negative. In fact, if you're dealing with measurements, you're always going to take the positive square root. And that positive square root is called the principal square root. It doesn't matter that it's called the principal square root, but if you hear your teacher saying it, that's what they're talking about. All right, now these are all nice and well, but we want to talk about irrational square roots. Square roots are super easy to simplify when we're taking the square root of a perfect square. So the square root of 1 is 1. Square root of 4 is 2. Square root of 9 is 3. Square root of 16 is 4. Square root of 25 is 5. Perhaps I put too many examples on here. Square root of 36 is 6. Square root of 49 is 7. Square root of 64 is 8. And thank goodness I ran out of room. Square root of 81 is 9. So you should know your perfect squares. And taking those square roots is really easy, right? You just have to remember your perfect squares. Now, square roots are not so easily simplified when taking the square root of a non-perfect square. In fact, you need a calculator to do them, all right? And I think I remember my father saying that they used to learn the formula when he was in school, but that's like a million years ago. So we do not do that. Let's look at an example of what I'm talking about. Let's consider the square root of 30. There is no whole number. Whole numbers are called integers. There's no whole number that we can multiply by itself so that we could square to give us 30. So the square root of a non-perfect square is what we call an irrational number. Yep, just like pi. Irrational values will need to be estimated. Okay, so how are we going to do that? Well, we're going to use the closest perfect squares we know. We're going to use the closest one below 30 and the closest one above 30. Hopefully you come up with square root of 25 and the square root of 36. Square root of 25 is 5. We've spent a little time with that already today. Square root of 36 is 6. So let me draw a little number line here and show you what I'm talking about. So if we look at this, and we're taking away the square roots for right now, we're just going to look at 30 is somewhere in between 25 and 36. Actually, 30 is in between 25 and 36. So the square root of 30 should be in between 5 and 6, right? That's how we got here. We want the square root of 30. We know the square root of 25. We know the square root of 36. So we know the square root of 30 is somewhere in between 5 and 6. Well, how close? Well, let's look. Between 25 and 30, the difference is 5. The distance is 5. And in between 30 and 36, the distance is 6. So 30 is just a little bit closer to 5 than or 25 than it is to 36. So the square root of 30 is slightly less than 5.5, right? Because it's just a little closer here. So I say 5.5 would be a pretty good estimate. Well, how are we going to check that? Well, we'll check by squaring 5.4 because we know it's going to be a little bit less than 5.5. So what's 5.4 squared? 29.16. Now, if we want to go a little bit further and check 5.5, because remember we said it is going to be somewhat less than 5.5. 5.5 squared is 30.25. Well, I said 5.5 would be a good estimate. It would be, but it goes over. And we knew it was going to go over. So I'm going to go with 5.4 as my estimate. Now, you could get out of control and start going to the hundredths and square 5.45 and see that it's 29.7. But for most purposes, tenths is fine, right? It's 2020. We could use our calculator if we really wanted to know what the square root of 30 was. But that's basically how you go about estimating those. So let's talk about simplifying, because you're going to use simplifying square roots much more often than you will estimating them. All right, so a square root expression isn't considered in simplest form until there are no perfect square factors of whatever number is under this radical sign. So this is not in simplest form. I can't give the square root of 18 as an answer on a test. It's kind of like giving 2/4. You wouldn't write 2/4, you would write 1/2. Okay, so what are we going to do? Well, we know it's not in simplest form because we know there's a perfect square factor of 18. We should know there's a perfect square factor of 18. So we're going to break up 18 under the radical symbol into two factors. We're just going to rewrite 18 as the product of two numbers. And one of those numbers needs to be the largest perfect square factor. So let's remind you, these are the factor pairs of 18. 1 and 18, well, this doesn't work because none of these are perfect squares. 2 and 9, 9 is a perfect square. This will work. 3 and 6, neither of these are perfect squares. They help us not at all. So I want to break 18 up into 2 times 9. And that's exactly what I'm going to do because 9 is a perfect square. So I'm going to rewrite 18 as 9 times 2. I haven't done anything here. I've just rewritten it. 9 times 2 is equal to 18. So now I'm going to break them up into two separate square roots or two separate radicals. Why did I do that? Well, because the square root of 9 is actually a whole number. And that's what I'm trying to get at. I want to simplify it as much as I can. So I'm going to write the square root of 9 as 3. I'm going to write the perfect square as a whole number, right? So I'm going to write 3 times the square root of 2. Now, we don't really use a dot or a multiplication symbol anymore. We know that if we just stick this 3 right up against the radical, that implies multiplication. So that's exactly what we're going to do. We're going to write 3 rad 2, or 3 times the square root of 2. All right, so let's practice a few of these. Square root of 48. Square root of 48 gets asked a lot because, I don't know why. I think because students are going to say 12 times 4 instead of 16 times 3. 16 is the largest perfect square factor that goes into 48, so you want to use 16 times 3. What if you used 12 times 4? Well, you would just have all these extra steps, right? It wouldn't be the end of the world. But we're going to use 16 times 3. So we're going to break it into two separate radicals, square root of 16 times the square root of 3. We're going to write the square root of 16 as 4. We're going to remove the dot and write it like big boys and girls, 4 rad 3. Okay, so here's what I'm saying. If you used 12 times 4, you would get 4 rad 12. You would say, okay, well, 4, that's going to be 2, but guess what? 12 also has 4 as one of its factors. So before I do anything, I'm going to rewrite 12. So now I have the square root of 4 times square root of 4 times 3, which gives me square root of 4 times square root of 4 times square root of 3. So you get the same answer, you just have a few extra steps. So if you don't choose the largest perfect square factor, don't worry. Square root of 75, so I'm going to pick 25 and 3. I'm going to break them into two separate radicals. Remember, the square root of 25 is 5, so we have 5 times the square root of 3, but we're going to write it without the dot, 5 rad 3. Okay, square root of 450. Anytime you get a number that seems unusually large, divide it by 2. Most of the times, they're giving you these huge numbers, and if you take 2 and divide it by 2, the other factor is a perfect square. As is the case here, 450 divided by 2 is 225. 225 is a perfect square. So we're going to write it as two separate radicals. Square root of 225 is 15. So we get 15 times square root of 2, and 15 rad 2 is our final answer. Now this one, it just has a coefficient as a number multiplied in front of it. That's fine. It doesn't actually give you any more work until the very end where you have to multiply that 3 by whatever you get. Okay, remember that this reads 3 times the square root of 108. So we're still going to simplify square root of 108 like we would if the 3 were not there. So 3 times 36 times 3. We're going to break those up into two separate radicals. Now we have 3 times the square root of 36 times the square root of 3. Remember, this 3 has to come with you for every single step. Don't lose this 3 out front. Square root of 36 is a whole number, 6. So we have 3 times 6 times the square root of 3, which gives us 18 times the square root of 3, or 18 rad 3. All right, so now we're going to simplify square roots that look a little different. Whoop, ignore this right now. I must have messed up my animation. Okay, we're going to look at square roots that have fractions underneath. For a square root expression to be in simplest form, you can't have a fraction under the radical symbol. So you cannot turn this in as your answer, the square root of 1/4. So for this, there's a rule. The rule states if you're taking the square root of a over b, it's the same as the square root of a over the square root of b. So if you have a fraction, you're going to take the square root of the numerator and you're going to put it over the square root of the denominator. All right, so that's just your rule for simplifying fractions that happen to be under a radical. So we're going to break this up into two separate radicals, square root of 1 divided by the square root of 4. Now they're both perfect squares, so this is kind of nice. Square root of 1 is 1, square root of 4 is 4. So the square root of 1/4 is 1/2. And technically it's positive and negative 1/2, but we're just worrying about simplifying them right now. Okay, so I just want you to check this. I think that maybe when I put the square root of 1/4 up, you knew 1/2 times 1/2 was equal to 1/4. So this wasn't earth-shattering for you. But remember, these are just numbers. We're just saying what value squared gives us this number under the radical. So you could check it. 1/2 squared is 1/2 times 1/2, which is equal to 1/4. It checks out. All right, So now we have the square root of 5/16. We're going to use our rule again. So the rule says break that up into the square root of the numerator over the square root of the denominator, and you get the square root of 5 over the square root of 16. Now, square root of 5 I can't do anything with. Okay, this is prime. I'm not breaking it up. But I can break up, or I can simplify the square root of 16 because it's a whole number 4. So I get rad 5 over 4, and that's it. I'm done. All right, let's look at square root of 27 over the square root of 25. What could I do with the square root of 27? Well, let's just hold that for a minute because I can do something with it. But the square root of 25 is the easier of the two because I know that's 5. So I have the square root of 27 over 5. But I can't leave the square root of 27 because it's not simplified. It has perfect square factors. 9 times 3 should come to you, right? So we're going to break up the numerator. Square root of 9 times 3, that's the same as 27, but we are going to write those as separate radicals. Square root of 9 is actually the whole number 3, so we're going to say 3 times the square root of 3 divided by 5. All right, last type of simplifying. Fractions can't have a radical in the denominator. So think about what radicals are. If you have a radical of a non-perfect square, it's an irrational number. We do not divide by irrational numbers. We don't leave them in the denominator until you get to calculus, and then all of a sudden it's okay to leave them there, but that's a few years away. So let's look at what we do. We have the square root of 4/5. I already know that the square root of 5 is going to be simplified. There's nothing I can do with it. So when I use my little rule I just learned, square root of 4 divided by the square root of 5, I can simplify the square root of 4 as 2, but now I'm left with the square root of 5 in the denominator. All right? When you have a radical in the denominator, we have to do something that's called rationalizing the denominator. It's just a fancy term that means we're going to take the thing that's irrational in a denominator and we're going to make it rational. When we do this, I like to say, remember when we created equivalent fractions and we multiplied by the same number in the numerator and the same number in the denominator? I call that multiplying by a glorified 1, right? When you have the same number in the numerator and the denominator, that value is 1. And that's exactly what we're going to do. We're going to grab whatever radical is in the denominator and we're going to multiply by that radical over itself. So the square root of 5 over the square root of 5 is 1. Multiplying by this does not change the value of this fraction. And that's the point. We don't want to change the value. We only want to find something to multiply by so we don't have a radical in the denominator. All right? So when we multiply 2 times square root of 5, we get 2 rad 5. When we multiply square root of 5 times the square root of 5, anytime you multiply identical square roots, you just get what's under there. Let's look at why. Square root of 5 times the square root of 5 is the square root of 25. Square root of 25, we already know, is 5. Whenever you square a radical, whatever is left under that radical, that's your value. That's what you're left with. Okay? Maybe I used too many words to explain that. If so, hit me up if that didn't make sense. But if you square a square root, squaring and square rooting, they undo each other. You're just going to be left with what's under the radical. Okay, the next part of this assignment had solving equations with irrational solutions. All right, so if you are solving an equation and it only has one variable, let's say it just has a single variable and that variable happens to be squared. Well, then we can use inverse operations because we now know what the opposite or the inverse operation of squaring is. So in this case, the opposite of squaring is taking the square root. Other than that, a is by itself. I don't have anything to add or subtract away or multiply or divide, so I'm just going to take the square root of both sides. The square root of a squared is a, and the square root of 11 is positive negative rad 11, right? Okay, let's look at one more equation. 2 more maybe. All right, so we have m squared minus 6 equals 34. We cannot jump right into square rooting both sides simply because we see m squared. What we first have to do is get that m term all by itself. So before we could square both sides, we got to get rid of the negative 6 that's on the same side of the equation as the m squared. So the opposite of negative 6 is positive 6, or the opposite of subtracting 6 is adding 6. Either way, we add 6 to both sides. We get m squared equals 40. Now the m term, like the variable term, only has the square. There's nothing else on the left side of the equation. So now we can take the square root of both sides of the equation. We get m equals positive negative square root of 40. All right, let's do one more. In this case, we got a whole bunch to do. Before we can take the square root of both sides, we have to get the x squared term completely by itself on one side of the equation. So remember, you always get rid of whatever's added or subtracted first. If I chose to divide by 4 first, I could, but I would have to divide this by 4, this by 4, and this by 4. And I could do that. It's just easier if I get rid of whatever is being added or subtracted, because I can only add and subtract like terms. So I don't have to add the 12 to 4x squared because it can't be done. I'm just adding it here and here. So let's add 12 to both sides. You get 4x squared equals 60. Now, how is this 4 attached to x squared? It's multiplied. Opposite of multiplication is division. So we're going to divide by 4. Okay, 4x squared divided by 4 is just x squared. 60 divided by 4 is 15. Now we are left with simply the variable term squared. So we can take the square root of both sides. And x equals positive or negative square root of 15. And that's it. That's everything that was in that assignment. If something else comes up and I didn't cover it, please send me a question. Remember, on my YouTube page, you can always send me questions. You can comment on videos. You can email me. My email address is right there. I hope this helped. I hope we all get out of quarantine soon, and have a great day.